All right, so now we're going to look at a bunch of these different relations, and we have an example here. We're trying to figure out the divide relation on Z. We want to figure out if it is reflexive, irreflexive, symmetric, asymmetric, and we're also going to look at anti-symmetric and transitive in a moment, but I'll have to make more room for myself to write it all out. And to be clear here, X is said to be divisible by Y if and only if X can cleanly divide Y. So for example, 10 divided by 2 is equal to 5. That just gives us a number, an integer. So therefore we would say that 2 is our X, 10 is our Y, and it is true that 2 can divide 10. However, it is not true that 3 can divide 10, because if we try to divide it, we end up with some fraction. And we will actually put up a more formal definition of the divide relation. Just know that whatever the result of the division is, it has to be an integer. So the first property we want to look at is the relation reflexive? And that means for all, this is the important part, for all x, it is true that x is divisible by itself. R here just represents whatever the relation is. In this particular case, we're talking about the division relation. But for example, is it true that 3 divided by 3, does that equal an integer? And yeah. And in fact, for almost every single number, it is true that, any number divided by itself is going to be equal to 1. So you might think that it is reflexive. However, 0 is an integer. 0 is in fact an element of the integers. And we know that we can not divide 0 by 0, so that is undefined. And that's essentially all we need to do to prove that this is not reflexive. We need one example, one proof that this is not true. Because in order for it to be reflexive, we have to say that this is true for all values of x, this property needs to be true. So we're going to say that this is not reflexive because 0 is an element of Z and 0 divided by 0 is undefined. Now we need to look at irreflexive, basically meaning that it is never true that when you divide a number by itself that it ends up with an integer. Which we obviously know that that is not the case because it almost every single time it is true. It is reflexive, apart from this one edge case where it seems to not be true. So we can't say that it's irreflexive, and all we need to do to prove that it's not true is find some examples. So 3 is a random number I'm picking. 3 divided by 3 is equal to 1. So again, we can say that this is not reflexive because 3 is an element of Z. And 3 divided by 3 is equal to 1, which means that it does in fact satisfy this condition that x is divisible by y. But all we really need is one example of x being divisible by itself to prove that the claim that this is always not true is false. Now moving on to symmetric. We want to prove that if x is divisible by y, then that also implies that y is divisible by x. And again, we just need to find two numbers that are part of the list of integers where this is not the case. And that will be enough to prove that this is false and it is not true. It is not symmetric. So for example, we have the numbers 3 and we have 21. Both of these are elements of the integers. And these are random numbers I picked. There are many, many more to pick from. But all we need is one example where we can say that x is divisible by y. So x does divide y. We can prove that 21 divided by 3 is equal to 7. We have an integer as our result, so it is evenly divisible. So that proves that this is true, but we do not have this case. This is not true. And whenever we have true implies false, the entire thing is going to be false because our y in this case is going to be 21, and we want to prove that y can divide x. So we would have 3 divided by 21, and you can definitely tell that we do not get a integer as our result. You'll get whatever decimal comes out of 1 over 7. So again, we've proven that this is not symmetric. Now, in order to prove that this is not asymmetric, in order for it to be asymmetric, this property has to hold for every single value of x and every single value of y. In order to disprove it, all we need is one example where this is not true. So we can say that we have negative 10 and positive 10. Both of these are elements of integers. They are both integers. We can say that our premise is true because 10 divided by negative 10, that's going to be negative 1. So we've proven that this part is true. But this part is saying that it is not the case that y is divisible by x. So if we swap them around, we get negative 10 divided by 10. We can see that this is negative 1, which again is an integer, so therefore it is the case that y is divisible by x. So therefore we've proven again that this is not asymmetric. So again, we have proof here of two numbers where this is true and this is false. True implies false, therefore we can say that this is not asymmetric. The next property we want to look at is anti-symmetric. What that means is that we have the case where x are y and y are x, where that implies x is equal to y. And we can use the same numbers again. We have that 10 and negative 10 are both elements of the integers. And we can say here that it is true that x is divisible by y. And in order for this premise to work, we need to say that both x are y and y are x, meaning that it is true that 10 is divisible by negative 10, which it is, negative 1, and it has to be the case that y is divisible by x. So again, negative 10 divided by 10 is equal to negative 1. So it is in fact true. We have that this premise is true. But for it to be anti-symmetric, we're saying that when this is true, it is always true that x is equal to y. But we can see clearly that 10 is not equal to negative 10. So this is a proof that it is not anti-symmetric. Now the only property left to look at is transitive, and it is transitive, so we're going to have to prove that it is transitive. Transitive basically means that if x are y, and y are z, then that implies x are z, which are elements of the integers. And here I'm going to do a concrete example because I think it helps to, look at. Let's say we have three values of x, y, and z, 10, 20, 40. So what we have here are our values of x, we have our y, and we have our z. And what we're saying is that x are y, meaning that if x divides y, which in this case what we're asking is does 10 divide 20? So 20 divided by 10, that is going to be equal to, and we have the case that y divides z, which if we look at 20 and 40, 20 does divide 40. Once again, we have 40 divided by 20, that is going to be equal to 2 once more. It is transitive if it is the case that x also divides z, meaning that 10 also divides 40. And we can see that if we have 40 divided by 10, that's going to be 4. This is true. But when we're trying to disprove something, we only need to find one example where the case is true. Here we have to prove it for every single value of x, every value of y, every value of z. Now another way of saying x divides y is to say that y divided by x is going to be equal to a, where a is some element in the set of integers. That is our definition. Because if a is not in our list of integers, then that basically means that it is not divisible. That means that a is some kind of fraction or irrational number or something that is not an element of the set of integers. And pretty much the same thing here. We have z is divided by y, and that is going to be equal to b. We don't know what the values of a or b are. They're placeholders for now, but we do know they have to be elements of the integers. So we can rearrange this and we can say that y is equal to a times x. Z is going to be equal to y times b. But we can see here that y is equal to a times x. We can plug that into here. So we have that z is equal to ax times b. And then all we need to do is divide both sides by x. So what we can see is that z divided by x is going to be equal to a times b, where both a and b are going to be elements of the integers. Therefore, we can conclude that the divide relation on the integers is in fact transitive.